Hello, my name is Fernando Garcia, and I'm going to be presenting on an explorative study of blockage challenges for implementing 5G wireless technology in smart manufacturing environments. For today's agenda, I'm going to be talking about my research background in 5G and smart manufacturing, the research goals and objective, research methodology, which is going to be the theoretical model of signal propagation, the simulation, and from this, I'm going to talk about the results and discussion, and then lastly, the conclusion. So first off, 5G technology. 5G technology is held for its transformative capabilities, offering several key advantages over its predecessors. Its ultra-fast speeds, low latency, and high bandwidth enable lightning-fast data transfers and real-time responsiveness, revolutionizing how we interact with digital content and services. Additionally, 5G enhanced connection density and ultra-high reliability ensure consistent connectivity, even in densely populated areas or critical applications. And for smart manufacturing revolutionized traditional factories by integrating cutting-edge technologies like Internet of Things, AI, robotics to automate processes and improve efficiency. Also, smart manufacturing has real-time data analytics drives informed decision-making, optimizing production quality and resource utilization. With wireless connectivity enabled seamless communication, manufacturing systems become more agile, capable of adapting quickly to changing market demands, and this approach fosters continuous improvement through predictive maintenance and digital twins, ensuring operational excellence and innovation in manufacturing operations. In my previous two slides, I mentioned the positives for 5G and smart manufacturing. However, there is some downsides, and the main downside is blockage. Well, 5G signal propagates at a higher frequency, which tends to have an increased absorption within blockers and obstacles. And in the manufacturing settings, obstacles could be metal machinery and equipment, the factory walls and structures, industrial interference, inventory and products, and the building layout and design. Even the operators themselves could be blockers. Now that we know that blockers is a big downside for 5G and smart manufacturing, this paper's goal is to investigate the feasibility of integrating 5G technology with smart manufacturing environments, addressing challenges related to signal blockages, and proposing a methodology to optimize signal coverage and enhance wireless connectivities. So our objective now is to develop a simulation model to analyze the behavior of 5G signals in the manufacturing environments and identify factors contributing to signal blockages. And lastly, evaluate the effectiveness of this proposed mitigation strategies in reducing signal blockages and improving wireless connectivity in 5G-enabled smart manufacturing settings. So for this blockage model in my paper, one of the biggest important idea is the line of sight. Basically, as you can see in this image right here, you have a transmitter and a receiver, and those transmitter and receiver have a height associated to them. And the transmitter right here, you can see that has a height associated of HT, and the receiver itself is an HR. And the distance between the transmitter and receiver is R. And the line of sight is basically means the line that connects from the transmitter to the receiver. And this line of sight, we could characterize it as the equation shown here. HM of x is equal to AX plus B. HM of x, the units whenever you plug in an x in, is going to give you the height at that line of sight, anywhere between 0 to R. However, as you could notice here, it's in terms of AX plus B, A being the slope and B being the initial location. But we don't want, and in math, we have an equation that has two unknowns. You need two equations to basically fully characterize it. And, fortunately for us, we know that at location 0, you're going to get just the height HT, and at location R, you're going to get the location of the receiver. So there you go. Two equations, two unknowns, solvable. And this gives us the equation of line of sight as HMX is equal to HR minus HT over RX plus HT. So now that we got that idea, the main concept is the line of sight. Now, in any facilities, we only care for blockers that are equal or greater than the line of sight. That is because any blocker that is equal or greater than the line of sight is going to block the signal of the 5G. An assumption we are making that if that blockers that block the line of sight will not allow any of the signal to reach the receiver. And blockers themselves, not all blockers have the same height, length, or width. So we're gonna assume that blockers have a distributed height, length, and width. Therefore, we must work with probabilities. Now that I explained the concept of line of sight and the blockers and how they affect 5G signals, this paper now goes into the computational simulation. So in our computational simulation, the variables that could be modified is the location of the transmitter. Wherever you place it, you could change. The receiver, you could also adjust the height of it. The distance between them, you could adjust, and also how many signals you send out from the receiver, and also the angle you send them at. So these are the 5 variables that we're gonna focus on, and from here you could see values. Those values are values that is going to go into a design of experiment, and because of those values that we have, we create 192 combinations, and we're going to be running a design of experiments, and for each combination we're going to run 30 iterations, therefore creating 5,760 individual trials. Now we'll look how the MATLAB code works. First of all, you can see in figure A, we're sending out rays from transmitter onto a sectional area that has radius, and point B, now that's going to be our blockers, random blockers with height and length, and also a random height. And from there, we see that when a ray passes through a blocker, it's going to first evaluate if it's equal or greater than the line of sight, and if it is, it's going to mark it as blocked. And if it's not, then it'll continue until it reaches R or it reaches another blocker, and then it evaluates once again. Now, after running all those 5,760 runs, here is the results that came about him. And you can see from these 4 charts the blockage probability, and you can see that if you adjust the distance between the transmitter and receiver, the larger the distance, the more probable the signal is going to get blocked. And also for cone angle, the bigger you make the cone angle, the more it's going to get blocked. And if you decrease the height of Rx, you're also going to increase the blockage. And if you decrease the height of Tx, you're also going to increase the blockage. Now that we had so many points, like we created 5,000 and so value points, we could do a regression model. And here on those variables that we were able to change, and we realized that all of them do have statistical significance, and therefore do impact signal propagation. And here is the results. And from those results, we are able to now understand much more clearly with this heat map, where it compares the probability against 2 variables. And as an engineer, it's very helpful in order to understand how to place them in a manufacturing facility. So lastly, we determined that all study variables do have an impact on signal blockage, and that modifying the transmitter and receiver placement and beamforming settings will improve the signal propagation in a manufacturing setting. And this model can help engineers to further understand their manufacturing needs by adjusting the design of experiments to their equipment specifications.